Okay, so we are studying equidistribution of sequences. So our sequences would be in 0, 1. Now, usually we take a sequence of real numbers and take it modulo 1. So to get a sequence in 0, 1. So maybe it is best to write all this as 0, 1 open, because just so that you think of it like we always did as the torus. Okay, so I mean, not that it makes a difference here. So it is, oh, I haven't attached my tablet. Hold on. Yeah, so we say that it's equidistributed if the proportion of points that falls in an interval I converges as the n goes to infinity to the length of that interval. Okay, and we proved one theorem, which is that if alpha is an irrational number, then you consider the linear sequence n alpha of real numbers and fold it to 0, 1. Then you get an equidistributed sequence. So there are, yeah, so this happens. Okay, and today I will want to do this. I actually said something, but I'm a little unsure whether at least one of or whether the leading coefficient has to be irrational. I'll come to that. So we will do this theorem today. But we had one thing to remember is we had this basic lemma that how to show equidistribution. Equidistribution is one way to look at it is that this measures mu, which is 1 over n summation delta x k k equals 1 through n, converges to uniform 0, 1 in the weak sense, usual convergence of measures. But we avoiding that language. Okay, we just take it more simply. But the key point here was that you can show equidistribution by just checking that 1 over n summation em of xk goes to 0 for every m not equal to 0. These ems are complex exponentials, and this is sufficient to show equidistribution. It's equivalent to, in fact, but this is the useful technique to show equidistribution of a sequence. And in case of n alpha, what happened was that was actually a geometric progression. So we took, if you take em of if xk is k alpha modulo 1, then em of x bar, I mean em of k alpha bar is e to the 2 pi I k alpha mod 1, but that is same as e to the 2 pi I m k alpha, because the remaining part is an integer and e to the 2 pi I m times the integer is 1. So you get this, and this is a geometric progression. You can sum explicitly, and whatever it is something divided by an n. So this thing stays bounded by 2, the numerator, and the denominator is non-zero if alpha is irrational, whatever you take. Therefore, this goes to 0. That was the complete proof. Okay. So everywhere this technique will be useful. We will always use complex exponentials to show equidistribution. Okay.
Sir?
Yeah.
Yeah, so is the second point that you mentioned there, is that related to that Monte Carlo integration?
This one. Yeah,
yes.
You can, I mean, so this is, for example, this says that you can use these numbers to do Monte Carlo integration if you want. So Monte Carlo integration, if you want to numerically integrate a function, I mean, of course, so how do you do it? One way is to pick equispace points and take the Riemann sum. Or you can take random numbers and take an average. But here is another sequence for which you can do. I don't claim that this is a good one. Actually, usually you have much better algorithms. So this is but the advantage of certain, yeah. So this is there. So so you have much better algorithms usually. But the thing about using random numbers and this kind of equidistributed sequences is, of course, the question of strategy. I mean, if you're thinking of integrating, so if you say I will take equispace points, then if I know that's what you're going to do, then I can give you a very bad function which will make you fail. Suppose I know that you're going to use 1000 equispace points, then I will take something like a sine function with frequency 1000, let's say. Sine of 2 pi times 1000x. So if you are going to take 1000 equispace points, then if I know that you are going to do that, then I can give you a function for which your estimate will badly fail, because you will get 0 at all those equispace points, whereas okay, in this case, it's not a good idea. I should take sine square, let us say, because the integral also is 0, but I take sine square, let's say. So then it's not like this, it's more like this. So then at equal-space points you fail, whereas don't. So that is one of the advantage. Random numbers actually do much worse in terms of accuracy for reasonable functions, but they are something you cannot mess with. Meaning that even if I know you're using random numbers, I cannot find a function which will make it fail badly, because I don't know what those exact random numbers you're going to pick are. Similarly, for the equidistributed sequence, they don't work well actually. But anyway, this basic one is not a great one anyway. But it is something that it will be hard for somebody who is trying to plan against to find strategically a function which will fail badly. But yes, in that sense, you may interpret it as something that will allow you to estimate an integral. If you have an algorithm that can evaluate the function at points, but you don't know how to integrate it, then this is a way you can calculate the integral numerically.
Thank you.
Okay. Any other questions? So then I'll go on to the next one, which is polynomial sequences, which is way more sophisticated. It's not this easy. So just to say here, for example, so if you want to do, so now we want to look at polynomial sequences. Example, alpha n square, where alpha is a irrational number. Okay, so is alpha n square this equidistributed? So the difficulty here is that Weil criterion says that enough to check goes to 0 for all m not equal to 0 integers as n goes to infinity. We want to check this, but the problem is this has no simple formula, right? So this is e to the 2 pi I m alpha k square k equals 1 up to n. No simple formula for this. Okay, how do you, I mean, the whole idea is, of course, that if your points are going all over the circle equally, then when you add these complex exponentials, that will kind of cancel, right? The cancellation is what is happening. But here, the cancellation, we didn't see the mechanism of cancellation. We just saw that it was a geometric series and summed it. But here, again, I can remove the alpha k square bar, I mean, because that's okay. But how am I going to do? But how will I find this? There is no formula for this. So it has to be much more, it is much more involved. Okay, it's more involved. So that's what we are going to do now. Is this okay? Okay. So here is the basic idea. So this is a nice lemma of Van der Kooput. What happened? Okay, so what is this lemma? So let X be a sequence in 0, 1. Greater than equal to 1, be a sequence in 0, 1. I'll write 0, 1 like this. So this is the torus for us now. Okay, suppose for h greater than equal to 1 integer, let xh be the difference sequence. Xh be this sequence XHK, which is defined like this. XHK is X K plus H minus XK. It is the difference sequence. So if H is 1, it's the first difference. If H is 2, it is the second difference. You take difference in this one. Okay. So it will be this. So the lemma is like this. If XH is equidistributed, okay, all this is, of course, you will take mod 1, right? Everything is mod 1. Everything you fold onto 0, 1. Okay. So is equidistributed. So taking differences of real numbers and then modulo 1 is same as taking modulo 1 and taking differences and then again modulo 1. Okay, so all these are hopefully clear. So folding you can do. So all this have to be done. If XH is equidistributed for all H, then the original sequence itself is equidistributed. Okay. So this is the way we are going to work with. Okay, so how is it helpful? I mean, so is that clear? I mean, so you have infinitely many sequences here, but they are differences. So you have to look at X super 1, X super 2, all these things. If all those sequences are equidistributed, then the original sequence is equidistributed. How will it help? So example. So let X and Xk be alpha k square, where alpha is an irrational. Okay. Now what is XH? K is alpha into k plus h square minus alpha k square, which becomes, so you cancel there and you get 2 alpha kh plus alpha h square. Okay, so now alpha h square, this is irrelevant. This is irrelevant means it's an overall shift, right? And we know that this is equidistributed by our earlier theorem. Because what is it? It is 2 alpha h. 2 alpha h is an irrational number. It is 2 alpha h times k. What we saw is that any irrational number times k, that linear sequence is equidistributed. Now you see that this is equidistributed because for every h, 2 alpha h is irrational if alpha is irrational. Right? So this is 2 alpha h, not in Q. So each xh so implies by van der Kooput by the lemma, it implies that alpha k square is equidistributed. See, I mean, so this is the way this helps. In general, this is the idea that if you want polynomials, when you take differences, you will get a lower degree polynomial, right? So that's the whole point. I mean, I may as well finish that off now. So as a corollary, let P of X be alpha d x to the d plus alpha 1x plus alpha naught with at least the leading coefficient. I don't know if I can say any coefficient, but okay, let me just state it this way. I'll come back to that. Suppose we assume that the leading coefficient is not rational. Then when you evaluate this polynomial at integers and fold it to 0, 1, this is equidistributed. Okay, so the proof is very simple, exactly like here. It's just induction. Okay, so if you take P of n, if you take P of n plus h minus P of n, what will you get? Okay, so it is alpha d n plus h to the power d plus blah 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 plus alpha 1 n plus h plus alpha naught minus you are going to subtract alpha d n to the d plus dot 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 plus alpha naught. Now you see that what happens is you will get n to the d minus 1. N to the d term will cancel because alpha d n to the d, alpha d n to the d, that will cancel. So when you take difference, you get a lower degree polynomial. Let me just write the first coefficient. The first coefficient is going to be, what will be the coefficient of n to the d minus 1? I can get it from here, the next term. So n to the d minus 1 times what is the coefficient? Let's just write that. The coefficient will have what all? It will have alpha d, and I have to take d times h to the d times h. That's the first one, right? So first you get n to the d plus d times binomial expansion d times n to the d minus 1h. That is what comes here. In the next term, I also get, oh, I get something with n to the d minus from here also, right? I get alpha d minus 1, and then I get here I get but that also cancels actually. Minus alpha d minus 1. Okay, because here also there is an alpha d minus 1 n to the d minus 1. So this alpha d minus 1 that will cancel actually. So it's good because plus some lower order term. So this is a polynomial of degree d minus 1 with leading coefficient what is the leading coefficient? It is alpha d dh. D is integer, h is integer. So alpha d is irrational, which does not belong to irrationals. So inductively by on h, induction is on d. Induction on d, it is equidistributed for any h. And hence, by the lemma, you get that P of n itself without the differencing is equidistributed. So that's how you go from differences to the. Of course, all the magic is hidden in the lemma. So it makes the whole thing very easy to do induction. The point is, why is it true that if from differences you can go to the sequence? So, but is this okay? I mean, for polynomials, then that's the only thing that is left to prove. That you have to show that if differences are equidistributed, then the original sequence is equidistributed. So that's the thing to prove. Okay, so we'll do that. So there is a main point. So we want to prove. So we now want to prove the Van der Kolk inequal lemma. So there is an inequality which I will state. It will. Okay. So proving. So how do we prove Van der Kolk lemma? So we want to look at, okay, so we have to look at fix m not equal to 0 and let Vk be, let's give Vk as e to the em of xk. So this is the sequence. So let's have a couple of notations, so which makes it a bit simpler. So Vh, then Vh k is of course vk plus h, which is em of x k plus h. Okay, so that is okay. So that is the these are the oh sorry minus. No, should I do it for okay, sorry, what was my h? H was for the difference, right? Okay, so then yeah, no, I shouldn't use the same for the shifted here. What I wanted is for a shift. What shall I do? I want to say a shifted sequence. I just want to introduce a symbol for that. What shall I do? Here I introduced h I defined for the difference, right? Okay, that's not good. Yeah, so what shall I call it? How shall I indicate? So V super H. Yeah, I don't know what symbol to choose now. I just want something that is V K plus H. Is okay. So for now, let me just call it UH sub K is V sub K plus H. Okay. So U for H greater than equal to 0, then actually that is conflicting notation. This looks like difference. So I don't want to do that. I shouldn't have introduced that for the difference. Yeah, I don't know what is a good symbol here for the shifted sequence. Okay, let me just go with this now. Let me just use
maybe
U.
you can just put the H in the like U sub H, right? You can just maybe call it
Yeah, that
maybe.
was conflicting with the the K down here. So maybe okay, maybe I will write every sequences as V of K. Okay. So yeah, maybe that is what I will do. So let's write V of K. So let's write the sequence as functions. So the kth element I will write as a function of, I mean, the kth, and then let VH K be V sub K plus H. Okay. Sorry, V of K plus H. Okay. So the shifted sequence. Of course, V0 is V, and VH for H greater than equal to 1 will be the shifted sequence. So now the point is what, and also we'll have these averages all over again. I mean, we'll have this type of averages. Okay, so maybe it is just easy to give it a name. So let's give sigma nv of any sequence. Sigma nu will denote 1 over n. K equals 1 up to u of k. Okay, so this is like a Cesaro average. So I just use this type of notation in Bayes' theorem proof. So I'll just use the same. Okay. So now what we want to do is, so the goal is to show that sigma nv goes to 0 as n goes to infinity, right? So that is the goal with this particular choice of v. So that particular v, we want to show this type of thing. So we'll come to that, but for now it doesn't matter. Actually, you can forget what that v is. We'll prove a certain lemma, but I don't want to write the lemma in the beginning. In fact, I'll have to remember. So we'll just do some manipulations. So for now, V is any sequence so I will not be using that it is actually the complex exponential. You will see in a moment. It will not matter that it is in the end we will put that. But so take any such sequence and VH, etc. as above. Okay, so some complex numbers with absolute value 1, and you do this. So we will want to consider sigma and V. So the idea is also to consider shifted averages. Okay, so let's look at sigma and VH. Is that same as sigma and V? What's the difference between these two? Okay, so you should think of in throughout, you should think of this H as somehow small and N as large. That will make the I mean, what is written is fine, but what to think of it. So imagine, what is this? This is the average of, so sigma n VH will be the average of the first n in the VH sequence, which means it's the average of VH plus 1 to VH plus n, right? Whereas sigma NV is the average of V1 to Vn. So you think of n as large, h as small. So what is the remaining? So the part that is left over here and left over here are to be thought of as pretty small. That makes this inequality clear. So this is actually bounded by, it's actually, well, the difference is in fact exactly equal to, what is this difference equal to? Well, okay, so let's just write a bound for it. I can write the exact, so the difference is the first h terms in V and the first h terms in, last h terms in VH, right? But whatever they be, they will together sum up to at most 2h. Even if I put all the absolute values, actually some come with a plus, some come with a minus, anyway they are complex numbers, but you put all the absolute values inside, this is at most 2h by n. Is this okay? So because it's the sum of 2h of the VIs. Is this okay? So that these two averages are pretty close if h is small. That's the idea. Okay. So what that means is that sigma n V, so I can, if I, so sigma n V and sigma n V1 shifted by 1, shifted by 2, shifted by 3, they are all pretty close. So sigma n V is going to be close to the average of these also. If you want, I can write sigma h, sigma n V. Okay, what does that mean? This means sigma n V minus, this is now a, sigma n VH is a function of h. Okay, so this is in the h variable. So what I mean is, if you average the averages of the shifted sequences. Okay, this is what I mean by this. Okay, so maybe this notation is not very clear because the second one is operating on the index h. Okay, so that means it's the average of the first h of the capital H of this. So h is some number, again integer greater than or equal to 1. So this one is actually, since each of these terms is close to this, okay, so this is going to be bounded by the sum of these differences. 1 by n into 2h, h equals 1 up to capital H, and that is going to be how much? That is capital H into capital H plus 1, so it is h plus 1 by n. So let's just write it as at most 2h by n. This is at most 2h by n. Oh, by the way, I didn't give references in this. I have my old notes also, but there is a book by Tao. So that, I mean, it's written in many places. Okay, there are entire books on this topic, but there is a nice book by Tao called Higher Order Fourier Analysis. Maybe at some later time I will mention what this higher order is, which I don't know myself, but why that is higher order. But the beginning part, very beginning part, is about equidistribution. So all of what we call Fourier analysis is linear Fourier analysis. Okay, first order Fourier analysis. So what this higher order is for later. So it's only the beginning parts of this book. I mean, pretty much it has a very nice presentation of this material. So I'm more or less taking exactly that. Okay. So this one will be
Manju, what happened to the h term in that? H times h, that last one. H times
this
h plus
cancels
1
with
by
this
2.
capital. Oh, okay. So there was a 1 by h here actually, because this is 1 by capital H. Actually, this is 1 by h into
Oh yeah, okay.
this thing is bounded
Yeah,
by
yeah.
this, and that is bounded by this 1 by nh into yeah, this was 2h by n, so that comes out and I get this 2h by n. Okay, is that okay? So this is pretty close.
Yeah.
So what we get from this is that, okay, so consequently sigma n v, if you, this is what we would like to bound, right? Sigma n v is bounded by, we want to say that this is small. That's how we get to equidistribution. So it is bounded by sigma h, sigma n vh, this thing. The meaning of this is here. Okay, I will write that, plus something like 2h by n. Okay, so we want to understand this, what this is like. So this quantity is nothing but, so the sigma h, sigma n vh is what? It is 1 over, it is 1 over h, 1 over n. So if we write it out, it is 1 over h, sum of h equals 1 up to capital H. And then this is sigma nv is itself an average. So it is 1 by n. Then you have k equals 1 up to n v of, but of vh. So it is v of h plus k. Okay, that is what that quantity is, right? So this is exactly this. Now you just interchange the sums. And write it as 1 by h equals 1 up to h, v of h plus k. So this sum is the, so we do the sum over h first and then do the sum over n. Okay, so that is, of course, everything is legitimate. It's a finite sum. So, but now this is an average, so you can use Cauchy-Schwarz and you get sigma h, sigma n, vh. That is bounded by, or if I put a square here, that is bounded by the average of the squares. I get the square of whatever is inside. So maybe, so is that okay? So this is just Cauchy-Schwarz. Now you expand it. I mean, so you expand this whole thing. So what you get is 1 by n. 1 k equals 1 up to capital N. We get 1 by h. Maybe I put the h square here. So 1 by h, capital H square comes outside. And what I'm left with is sum over h1 and h2. So sum over h1 as well as h2 running from 1 up to capital H. So you get v of h1 plus k. There is an absolute value square. These are complex numbers. Okay, so even if our original sequence are real numbers, we are going to apply it to complex numbers. So conjugation is very important here. V of h2 plus k bar is okay. So this is what we get. But now you can kind of, so you look at, you interchange this again. Now you interchange back. So you get 1 by h square h1 h2 equals 1 up to h, and then 1 by n k equals 1 up to n, v of h1 plus k, v of h2 plus k conjugate. Okay, so you get this. This is an inequality for this quantity, and this we have to finally take square root, and then we'll get a bound for sigma and v. Okay, so what is this going to look like in some way? So this is, so this one. So let's look at a couple of cases. So when h1 equal to, so inner sum. So this whole thing. Now I am going to concentrate on the inner thing here. So the inner sum. when h1 equal to h2. What happens when h1 equal to h2? When h1 is equal to h2, you get 1 by n, sum of k equals 1 up to n, you get 1. Because all vk's are, so this is actually 1. Because we assume that vi absolute value is 1. So that term h1 equal to h2 will give you 1. And there are how many such terms are there, by the way? There are n such terms.
H such terms.
Oh, sorry. Number of such terms is h, not n. Yes, thank you. So this is number of such terms, h1 equal to h2. So if for each of 1 to capital H, you get 1. Now you take when h is not h1 not equal to, when let's say h2 equal to h1 plus h, let's say, and h greater than equal to 1. What happens? What is that inner sum? So we can write it as it is Vn of V of h1 plus k and V of h1 plus h plus k. K equals 1 to n, right? But again, it is more or less same as this shift. So it is some V summed at some numbers and V summed at the shifted numbers.
So the conjugate is missing.
Sorry, the conjugation is here. Thanks. The conjugation is here. So we can do, instead of summing from, so can I just, how close is this to, if I just, the point is to say that it depends only on the difference, right? I mean, so what I want to say is that this is more or less the same for any h. It depends on the difference. Why? Because it is V summed at some numbers and V summed at the same number shifted by h. Of course, but these numbers are slightly different. So if I want to do this, so this is not exactly true. Okay, this is exactly like before. I mean, like here when I did sigma n v h and sigma n v, one was summing from v1 to vn, another was summing from v of h plus 1 to v of n plus h. Here, similarly, we have difference between h1 and I mean, so this is actually, so this is, there is a remainder term. So let's write our h1, h2. Our remainder term, okay, it won't depend on anything. Okay, let's for a moment write it as our h1, h2. It depends on h1 and h2. But what is the bound you can write for our h1, h2? Okay, what is the difference between these two things? Well, there are the terms here which these ones start at h1. So here they start at h1 plus 1 and go up to h1 plus n. Here they start at 1 and go up to n. So what's the difference? So this is actually, there are h1 terms here which are missing here, and there are these last terms. There are h1 terms here which are missing here, and conversely there are h1 terms here. So this is actually bounded by 2 over n h1. Is that clear or not? So which we can just say is bounded by 2h over n. Is that clear or am I being confusing? So it's okay. So all I'm saying is this, all the terms are of absolute value 1. Okay, so terms are of absolute value 1. So the only question is how many terms are different. So there are h1 terms here that are missing here, and there are h1 terms here that are missing here because of the shift. So the total of those will be 2h1 at most, and there is a 1 by n outside. So and h1 is anyway running from 1 to capital H. So this is bounded by this. So this is all we need. So it's the same, similar when h2 is similar when h1 is h2 plus h. H greater than equal to 1, except the whole thing is conjugated. So what we get here is that 1 by n. So if we take the other way, this is, h1 is h2 plus h, then what will we get? V of h1 plus k, V of h2 plus k bar. this will be exactly the conjugation of this. So we will write this as 1 over n v of k plus h conjugate k equals 1 up to n, and the whole thing is conjugated plus the same remainder term conjugated. Okay, and this is bounded by this number. So what I have done is for each of these terms, I have figured out what this is going to be. So the h1 equal to h2 terms will give me 1 each of them, and there are capital H many such terms. So when h2 is bigger than h1 or h1 is bigger than h2, you will get conjugate. So once it's enough to analyze one side. When h2 is h1 plus some small number h, then this is, you can write it as this vk plus h bar plus a remainder term which is bounded by 2h over n. So what is, and how many such terms? That also we need to analyze. How many such, number of such terms is, see the difference. So h1 can go from 1, 2 onwards, but h2 has to be within n. So h1 can go up to 1, 2 up to n minus h, right? So the number of, 1, 2 up to capital H minus h. So it's capital H minus h or something like that, right? Plus 1. Anyway, it is bounded by capital H. That's all. The number of terms is at most capital H, because you start with a difference. So you can, h1 can go up to 1 to capital H minus small h or something like that. So with all this, what do we get? So this whole quantity, now let me analyze here itself. With all this, we will get that this is bounded by 1 by h square. And let's take the equal terms first. There are h terms. H terms which are all equal to 1, h into 1 plus, what do these two terms together give? These two terms together will give me this quantity. Okay, so, well, what do I get? Plus h times, what do I want? What do I get when I add these two? So maybe I do that here. So add these two. The sum will be, you add this and this. So you'll get 2 over n times the real part of k equals 1 up to n vk plus h bar plus some remainder term 2 times. So again, okay, so you get 2 times the remainder term. So whatever it is, so this is of course in absolute value it is bounded by 2 over n. Absolute value of this sum is bounded by 2 over n. Let's just put absolute value. Real part and absolute value, they are pretty much, so you bound it by the absolute value. That is one term. And then you will be left with 2 over, what is it bounded? 2h over n. So you'll get 4h over n. So each of these terms, when you add h1, h2 and h2, h1 terms, I get something like this, right? So I have to put this here. So what do I get there? So I'll get, again, how many times do I get? I get at most capital H times, right? The number of such terms is at most capital H. So let me write here capital H times that whole quantity, which is this one, 2 over n k equals 1 up to n vk plus h conjugate, but we put an absolute value on this, plus the remainder term, which is something like 4 times h over n. All the constants are completely irrelevant. Okay, which is equal to what is it? Let's just write less than equal to one of the terms. The h and h cancel here, so we'll get one of the terms we get. Oh, but then I forgot to sum over small h. Sorry. There is also the sum I have to. So I was fixing h2 minus h1 equal to small h, but then I have to sum over all the small h's. So that I forgot here. I get plus capital H, but then I also get a sum over small h equals 1 to capital H. So let's take that term first. So 1h cancels here. So I'm left with 2 over h. H equals 1 up to capital H, and then 1 over n. Summation k equals 1 up to n, absolute value vk h bar. Okay. And then I'm left with some error terms. So here I have 4h by n. Actually, that is also getting multiplied by 4h square by n. So that will give me 4 by n, right? So that will give 4h square by n. So I will get 4 by n. Yeah, so that will give me 4 by n plus what will this give me? Plus 1 by h. So I'll get something like this. So the average of this is giving. Okay, so if this detailed thing was not easy to follow, but you have to go through it, then it's not complicated at all actually, but maybe it's not best to follow it when someone else is writing it. So, but you just take this now. So sigma h, sigma n v, this squared is bounded by this whole thing. So, and so we go back to this star actually. Okay. So we want to bound the absolute value of this by this. So what is it that we want to do? So now I'll write the bound. So sigma n v. So star says that sigma n v is bounded by sigma h, sigma n v h plus what was the quantity here? So 2h by n. Now for the square of this we have this bound. For the square of this we have this bound, sum of 3 terms. But you know, how do I have to take a square root, but that is okay. A plus b plus c square root is bounded by square root a plus square root b plus square root c. Okay, because when they are all positive. So we'll just bound it by the square roots of the terms. So what are the terms? So first term square root. So I get square root of, this is the important term, 2 over h. Sum over h equals 1 to capital H, and then 1 by n. A v a plus h conjugate. K equals 1 up to n. Then what are the other terms? I take the square root of this, square root of 4 by n plus 1 by square root of h, and then I have an additional term 2h by n. So, well, so this is the van der Kolk inequality. So this we can summarize and van der Kolk inequality. This is the way. So that this exact thing. See if okay, so maybe we'll just make one more. This was fine with any h, but let's assume if h get and vi, remember these are assumed to be of absolute value 1. This is important. Yeah, that is important. So we assume that. So then to get that sigma n v is bounded by square root of 2 over h sum over h equals 1 up to h. I could write it as sigma h, but let me not do it. But this let me write as sigma n of v times vh. V times vh bar. So this is V, this is the pointwise multiplication, K and Vk plus H bar, right? So it is just that. So it's the pointwise multiplication. Plus whatever I have here, what can I say? So H over N, I think I made a, did I get as 2 over square root n here, or did I make a mistake? Why did I get 4 over n? 4h squared over n. Yeah, so that was 4 over n. Or should I have gotten 4h over n? It looks okay, but we will just bound it by 1 by square root of h. And then yeah, so this one we can just bound it by, let's say, 4 times square root of h by square root. It's usually written like this. Maybe I missed the square root somewhere. But anyway, if h is smaller than n, h by n is smaller than h square root of h by n. So this is called the van der Kolk inequality. Okay, it doesn't matter. You take it in this form. Any questions or comments so far? So the details, maybe it is good to go over oneself, then you get it. So the point here is that I wanted to give a more clean interpretation of this, but I could not think of. Somehow this is like the, so the point is this term is like the correlation between V and the shifted sequence. V and V. They're complex, so you have a conjugation, but it's like the correlation between V and VH. So in some sense, what this inequality tells you is that if V and its shifted sequences are approximately independent, in that the correlations are small, then the original sequence is sort of equidistributed. That is what is being said, but I couldn't give an intuitive explanation for this. So anyway, we have this type of inequality. Okay. So we have this inequality, and yeah. So okay, but what is the point of this? Now it's very easy actually. Now you go back to, now we want to apply it with our shifted sequence, right? So to prove the van der Kolk lemma, now let's return to the proof of van der Kolk lemma. So here Vi is, Vk is Em of xk. Is e to the 2 pi I m into x. Okay. So now what happens? So now we get that, let's write it out all the things. So what we have is by this. Of inequality, what we have is that 1 over n, sum over k equals 1 up to capital N, Em of xk is bounded by, what is the first term? You have square root of 2 over h, sum over h equals 1 to capital H, and what is this quantity? Inside the absolute value, we have 1 over n, k equals 1 up to n again. What is V dot VH? So here VH of k is going to be e to the 2 pi I m x k plus h, right? So when you do that with its conjugate, what you see here is that Em of xk minus xk plus h. What we have here. Okay. And so that whole thing is under the square root plus 1 by square root h plus some constant times square root h by square root h. Is this okay? So now you see that one side you have the sequence, other side you have the differences. So this is also sometimes in some places they call it Wales differencing trick. I don't know exact attribution to give, but in other places it is called van der Kolk inequality. But you see, when in this form you don't see the differencing, but when you put V to be complex exponential of xk, then you see sort of the difference between the sequence and its shifted sequence, right? So that is where it happens. So now let n go to infinity. Fix h, and let n go to infinity. So by equidistribution of xh, we get 1 over n summation k equals 1 up to n, this thing, this whole quantity, em of xk minus xk plus h, that goes to 0 as n goes to infinity. So this goes to 0. This third term also goes to 0. So what we get
So
is,
I think Manju, it should be x super h, right? Because shifted sequence, that was your notation.
yeah, actually now I kind of went back to x of k minus x of k plus h. Yeah, actually, sorry. Yeah, maybe since yeah, there was that confusion. So let me write x of k minus x of k plus h. Which is, yeah, which we can write as, actually that is x, yeah. So if I go back to that original notation, that is em of xh of k, or minus of that. Okay, this is actually same as this, the difference. So that goes to 0 for each h. Okay, so therefore what we get is that lim sup em of xk absolute value as n goes to infinity is less than equal to, this capital H is anything, you have fixed h and done this, so this goes to 0, each of these terms goes to 0 and finitely many terms, h is fixed. So this gives me 0, this gives me 1 by root h, and this is 0. So you get this for any h. So implies that this also goes to 0. So that's it, done.
It's 1 o'clock.
Okay, so that proves the Van der Kolk inequality, and so this by Weil differencing trick, this is what we wanted to show, and that's done. Okay, so we have proved everything actually. So we proved the Van der Kolk. So key thing is Van der Kolk inequality. This is the main technical step. From Van der Kolk inequality, we get that if differences are equidistributed, then the original sequence is equidistributed. And that goes very well with polynomial sequences, because for polynomial sequences, differences will be lower degree polynomials. We have done the base case last time, and this with this you can do the induction step. That completes the proof. So I'll stop here. Any questions, comments? Happy to take.
Just a slight correction in